So now let me say something about what are called the Morse inequalities. Okay. So if you think about what happened when we constructed these complexes out of stable manifolds of, it's like the Morse male functions, right? Then you know that basically the number of, shall we say, simplices of dimension k are related, actually really just the number of critical points which have index k, okay? And of course it's like when we discussed things like the Euler characteristic, you know that the Euler characteristic is really just the alternating sum of the number of cells of each dimension. So what you might not then find so surprising then is that in the sphere example which we had, right, where you had this, and then this was a sort of a D, sort of stable D manifold, and then sort of paired with the stable zero manifold, right? And the stable zero manifold obviously is just the minima. It's like, and then the stable D manifold is associated with the critical point, which is the maximum, right? And you know obviously that maxima have index, it's like, which is D, which is the dimension of the full space. Okay, so so in the D sphere case, right, you just have one zero cell, it's like in one D cell, if you will, right? The alternating sum of the number of stable manifolds of each dimension, right, is 1 plus minus 1 to the D, right, which is the Euler characteristic of the D manifold, of the D sphere. Okay, and then more generally, as you might expect, the alternating sum of the number of stable manifolds sort of by dimension, if you will, right, give the Euler characteristic. And then this is what is called the strong Morse inequality. Sort of one of the strong Morse inequalities. Okay. So we're going to state both the strong and weak Morse inequalities. And instead of thinking about the number of stable manifolds by dimension, we're going to look at the index of the critical points. Okay. So we'll sort of consider sort of the strong and weak Morse inequalities. And sort of let CQ be the number of critical points of index Q. Okay, All right, so let me just state the Morse inequalities now. Okay, so M is a manifold of dimension D. Then F, which is a map from M to R, right, is a Morse function. Then the following is true, right? The first one is the weak one. It says that the number of critical points of index Q, right, is greater than equal to the Betti number. It's like the Q-Betti number of the manifold for all Q. Then the strong ones say that the sum is alternating sum of the number of critical points of index Q. So sum Q equals to 0 to J of minus 1 J minus Q of CQ is greater than equal to the sum, the alternating sum of the Betti numbers. Okay, minus 1 J minus Q beta Q of M, and this is true for all J. Okay, then the remark is that when sort of for 2, right, when J is equal to D, we have an equality instead of an inequality. Okay, because when J equals to D, it's like this is that alternating sum. It's like of the number of Q stable manifolds, or stable Q manifolds. It's like, and then the right hand side obviously is just the expression for when J equals to D. The right hand side is the expression for the Euler characteristic. Okay, and we had sort of said in words here at least that when you do this alternating sum with the number of stable manifolds by dimension, you get the Euler characteristic. Okay. All right. So let's try to show that the strong inequality implies the weak one at least. Okay. And then you won't have time to discuss this. It's like in this class, but the strong Morse inequalities, is considered in the book in the case of looking at piecewise linear sort of functions, right? So the basic idea is that if now it's like instead of having a manifold, it's like you have a triangulated manifold, right? Then it's like you can start looking at piecewise linear Morse functions, and then try to establish it's like these sort of strong Morse inequalities in that setting. Okay, so I won't have time to talk about that, but hopefully at least the discussion of the continuous theory, it's like gives you sort of the necessary background to better understand that section on your own. Okay, so anyway, so let me at least try to show you how the strong inequalities imply the weak inequalities. Okay, so all right, so if you take the sum from Q equals to 0 to J, right, which is sort of this term here, minus 1 to J minus Q, CQ, this is greater than equal to this right-hand side, right? So it's greater than equal to sort of beta JM. So I'm going to take out this one term here, and then subtracting off the sum from Q equals to 0 to J minus 1, right? Minus 1 to J minus Q minus 1, beta Q of M. Okay, and Okay, and then we can apply the strong Morse inequality to this term, right? So this term, in particular, I can multiply both sides by a negative sign. That changes the sign here, right? So this would be then greater than equal to beta j m minus sum q equals, q equals 0 to j minus 1 minus 1 to j minus q minus 1 CQ. Right, so so this is greater than this, right? So if I subtract off something which is larger, right, then obviously this is going to be larger than this, right? So that's just applying the strong Morse inequality twice, right? The first one, just this is just this right-hand side, but I've plucked out the very first term and then left the remaining term. This remaining term, I'm going to apply the strong Morse inequality again. It's like to give me the second inequality. And of course now it's like this here, right? This is of course nothing more than this is nothing more than Cj, right, minus the sum from q equals 0 to j minus 1 of minus 1 to the j minus q minus 1 CQ. Right, so this is greater than or equal to this, which means that Cj is greater than or equal to beta j m, which is what we wanted here, right? Yes. Okay, so that's the Jth sort of weak Morse inequality. Okay, all right, so let me just stop here for now.